about CNN acceleration on FPGA. So first of all, what is FPGA? FPGA is a field programmable gate array. It's an integrated circuit contains of a lot of semiconductors, and it is designed to be reconfigured by customers in the time of usage. Usually it can be described in HDL, hardware description languages like Verilog and VHDL. And it's important thing that we don't program FPGA, we just describe the architecture using these languages. Also, it can be designed on a lot of abstraction layers from the lowest logical gates and or not up to uh, higher things like arithmetical logic unit or DPU, deep learning processor unit. Uh, Also, it can include on-chip memory. Uh, it can include simple flip-flops or something more complex. And sometimes it is used to create ASICs. Now, what is CNN? CNN CNN stands for convolutional neural networks. Neural network is a graph with connections and weights on of every connection. It consists of a lot of layers. You can see on the picture below that layers can be some operations, convolution, ReLU, pooling, or normalization, batch normalization, instance normalization, or something else. Usually CNN is used uh, to process videos or images in real time, or simple process videos and images, and we use it in classification tasks. For example, on the image we have on the input some image car, and on the output we have the word that describes that this is a car. And this particular neural network is for classification different kinds of cars, truck, bicycle, something else. Convolution is the main operation in convolutional neural networks. Convolution is math operation on two functions, and the result is the third function. And this third function shows how the first function modifies the other one. On the picture, you can see that we use in convolution process we use some metrics. In image processing, we use the image as a matrix, m over n, and we use small kernels. It can be from one up to many kernels, 3 by 3, 4 by 4. It have to be square, and the result is some smaller metrics that shows some features of the input image that is get by applying the kernel. Now let's speak about most popular approaches of convolution. We will start from different frameworks. There are a lot of frameworks to deploy our models on FPGAs. OpenVINO. OpenVINO is an Intel project. VINO stands for Open Visual Inference and Neural Network Optimization. OpenVINO is a product for heterogeneous systems made by Intel, and from the very beginning they used it to accelerate to run and accelerate the neural networks on CPUs and GPUs from Intel. And then after Intel bought Jurassic Corporation, it is also possible to use OpenVINO on the Jurassic FPGAs like the 10 Nano or some else boards that you can know. Mipsology. Mipsology is a startup. This startup have a product called Zebra. Zebra is a deep learning compute engine for neural network interfaces, and this is something like OpenVINO, but for more platforms, because OpenVINO can be used only for Intel products. So they told that any model trained on your computer can be deployed using Zebra on different platforms that they support. And their main partner is Xilinx, now AMD, because AMD bought Xilinx. And they told that they have no change, they made no changes in the process. Everything is done by Zebra, and the programmer should not modify his network to deploy it. And they told that accuracy loss is about from 1 to 3%. That is not a huge difference. Now Xilinx. Xilinx is a corporation that have few frameworks to deploy the neural networks on the FPGA. VTSAI is the first. VTCI is a platform that is known from the 2019, and it is a development platform for AI inference on Xilinx hardware platforms, and also as far as we have Xilinx boards in the cloud, so we can run it in the cloud and on the FPGA. It supports model designed on Caffe and TensorFlow as and the documentation say that uh, uh, PyTorch models can also be deployed on the Vitis AI, but as far as I know from my experience, PyTorch models can be only uh, quantized on this Vitis AI, but there are no known solution how to compile, optimize, and deploy it on the boards. So I don't write this in the presentation. And also they told that the usage is very simple for all developers who are not in embedded spheres. So you need to just add something. You need to add a few imports and few lines in your model on Python to run it on the GPU. That is also a part of VTCI, but it's a hardware part. And it has a lot of documentation in the GitHub and on the official site. Also, it has an open source part. It's not fully open source because on the very top of each document there is a license that you cannot change the code. You can just read it to analyze what problems you have, and you cannot share the code. So it's a little bit it's a little problem while working with this framework. And also the other disadvantage is that it officially supports only 3 boards, but as far as the part of code is open source, it is possible to add more boards. For example, I have been working for 3 months with a board that is not officially supported, but it's very easy to write few scripts and deploy any model on this particular board. And for other boards, it can be um, simpler or harder, but it is possible. And Pink is another framework from Xilinx. It fully open source project, and it let you test your code, test your model in Jupyter notebook using Python language only, and also that deep processing unit that I mentioned before. It use parts of VTCI, for example, this DPU, and it has 8 officially supported boards that make it maybe simpler for beginning, because these boards are cheaper, and it's easier to work with them because you only need to change the chip in the Jupyter notebook settings from the CPU or GPU to FPGA, and add some more lines in your code, and also add some more libraries in imports. And also it's easy and fast to deploy models, but it's not a real solution and not a real product, because these approaches will be very um very slow, and they it is possible only to test the neural networks in such way. Okay, now let's talk about low-level approaches of calculating convolution on the FPGA, because convolution consists of some operations, and we can change this operation matrix multiplication using some functions as into call. We can reduce our input image matrices and kernels to matrices that can be multiplied, and repatch operation to repatch the output matrix, and we will get the result of our convolution. So the pros of this approach is there are a lot of uh, there are a lot of ways to accelerate matrix multiplications, but cons of this approach is that it needs additional operations into call and repatch that take a lot of time, and this approach cannot be can not be faster on some boards. For example, this it says for FPGA, if we will use simple matrix multiplication on FPGA, it will be much more slower than the same approach on the GPU, because GPU is the best for matrix operation over on matrices, and for matrix multiplications. And CUDA kernels has these SIMD approaches, single instruction, multiple threads, that that helps to accelerate matrix multiplication on the GPU, but FPGA have some different structure that makes it impossible to use simple matrix multiplication. So we have to use quantization. What is quantization? Simple model without any changes, have only float 32 weights and layers that operate with these float 32 numbers. So let's try to reduce our float 32 to int 8 or int 16 or float 16, uh, because we need a lot of power and a lot of memory to save float 32 numbers and that layers. By reducing our numbers to int 8, the result model will be faster. The and model will be not so weight, and we will save the same accuracy as before. How to do that? Every framework have its own approach to quantize. For example, TensorFlow that you may know can have its own supervised and unsupervised post-training to quantize the model, and Xilinx with this AI have part of this with this AI called Quantizer that help to reduce such numbers. It also a post-training, and for each model for PyTorch, TensorFlow and Caffe models, the process and input data will be different, but the result is quantized model that you can compile and deploy on the GPU on the FPGA. And also it is necessary to transform not only weights but also operations and lawyers. And that's why when you write any model that you want to deploy on FPGA, you need to use only that lawyers that are supported by the framework that you want to use to quantize the model. It's important thing, and you need to check the documentation before start developing the model. And ABM-SpConv, it is accumulate before multiply sparse convolution. It's a very new approach that is from the article 2019 year. It is it is a process that is have some difference from simple matrix multiplication because they not they don't use im to call and repatch operation. They just use convolution on the FPGA, but with some different convolution operation consists of multiplications and adding the result after multiplications. And they found that it is possible to make this operation, to separate these operations and to multiply all needed numbers, and they add them. What is more, they use on-chip memory to cache the results of multiplication. And in the output, we have that if we use the same kernel for the image in different parts of this image, the numbers can be the same in different parts of the image. So in the result, we multiply the same numbers twice or three, four times. They have pre-processing of the convolution that calculates the number of uh, entries, each number in the input matrix, count it and sort it in some way, and save these results in the table on the on-chip memory, so that when the model see something like multiplication of two known numbers, it just take the result from the table and don't do the multiplication. On the pipeline, in the on the pipeline, you can see that the time can be reduced up to from 2 to 3 times. And the best in this approach is that they use from 38 to 50% of DSP blocks, and the same about on-chip memory, because all articles about neural networks acceleration and all experiments in the articles use from 98 to 100% of DSP blocks and memory, so it makes impossible to have something else uh, on the chip, but only the parts that use convolution, and this approach leave half of board free, so you can use this space to deploy something else on the board. And in this approach, only first iteration, first applying of the kernel is very slow, and all other operations are faster and faster. And maybe the best for now approach is Vinogradov group of algorithms. Vinogradov, the very first variation of this, the very first iteration of this algorithm called Strassen algorithm, but Vinogradov is the person who accelerate the matrix multiplication from n cubed to n in 2.3. It's much more faster than everything before, and Vinogradov approach was the fastest known matrix multiplication approach for 30 years. And in 2010, math people start to make it faster and faster, but the faster approach is n in 2.36, so the result is not so huge as Vinogradov did. That's why this group of algorithms called Vinograd, sorry. And as you can see on the slide, for 2 by 2 matrix, the naive algorithm for 2 by 2 matrix multiplication, the naive algorithm require 8 multiplications and 4 additions. Strassen version of this algorithm requires 7 multiplications and 18 additions, but Vinogradov required 15 additions. So for small matrices, you use only addition without multiplication operation to multiply matrices. Why it can be faster? Because uh, as far as I know, both GPU and FPGA uh, have more units to make addition than multiplication, and that's why it can be the big deal to. It can be very useful to reduce the number of multiplications, even if it will increase the number of additions. And there is no differences in time for FPGA for different designs. For designs that use GEMM or Vinograd algorithm, we don't speak about ABM-SpConv here because it's from an article that compare only GEMM, VTSAI, and Vinograd algorithm. But the big difference is that resource utilization and power consumption the uh, is the better using this Strassen-Winograd algorithm, and uh, in real life, as far as we use not all FPGA for neural network, but we want to have something else on it. Other approaches can be much more slower. The same about multiplication units and addition units. And for this reason, yes, Strassen-Winograd is the best known approach to accelerate the CNN on the FPGA. And also there is one more algorithm called Coppersmith-Winograd. You can check it. It is more interesting, but it gives acceleration only for such big matrices that are not used now and that cannot. So this algorithm called like universe or something like that, and is not used in our life. So thank you for attention, and have we more time for questions?